Hi everyone again. My name is Razvan Crainea. I'm along with my colleague Liviu will be showing you the top challenges we've met while trying to build to grow to go global with some of the platforms that we've developed. First of all, both of us are core developers of the OpenSIPS project. In case we come here to ClueCon every year, so we've met a couple of times. Probably met a couple of times or we've seen around. And yeah, let's get started. So we'll be talking about going global. Today we'll be talking about going global and the problems that you might face when trying to scale out a platform. Our solution, we've done what we've done in OpenSIPS to help you do that as easy as possible, and then we'll get a use case based on our development, a use case how to build a distributed SIP registrar using OpenSIPS 2.4. So why go global? That's very simple. You want to scale out, probably horizontally, because you want to bring more customers to your business, and you want to get out of the small community that you started your business from. And you probably soon find out that one single server doesn't scale out. You can't bring all the, let's say, USA people. You can support all of them using only one server. So you start adding more servers, probably in different areas, in different geographic locations, in order to improve the call quality for your customers. You want to put the servers as closest as possible to them. And then you end up with something like this, where you have several nodes spread all over the country or your area of interest. And in order to ensure the quality of your services, you have to make sure that whenever a client joins the network, he will choose the best server. And usually this means the closest one, right? This has been done up until recently using DNS, using SRV records you've probably used that have different priority, weight-based methods that can help you decide the server that you might use. Also, GeoDNS servers, you probably have experience with that as well. However, probably most of you also experienced that. No, not all the clients fully support DNS, not all clients fully support SRVs. And even they do support it, they don't usually properly implement it. They use all sorts of cache that basically breaks everything that you want to do. That's why Anycast came in. Right, Anycast came in from the routing world. The guys that usually spend time configuring routers and stuff like that, not doing high-level applications such as SIP. And this method is used to basically allows you to present your clients the routes so that they reach your closest server. So you have different servers across the world. For each of them, you can specify different route sets in order to in order to aid them find you easier. This means that you don't have to rely on their algorithms of choosing your server. You will basically impose a single IP, a single route where they can connect to. And this is very nice because you can also do proper load balancing. You can, you by yourself can advertise different routes based on the load that you have on each server. You can also ensure reliability, and we'll see further on how to do that, and so forth and so on. It's very easy to do maintenance. For example, if you want to take out a node, simply pull that route out and nobody will connect to it because nobody will find it in the route set. So Anycast is a very, very nice mechanism. And how does it work? Anybody using it? Do you know how it works? Imagine that you have a single IP set on 3 different nodes. So here we have 3 different nodes in 3 different locations and only one IP assigned on that it can be found on each server. It might also have its unicast IPs, but we are not interested into that. So there's one IP that is shared among different nodes. When a client calls, he will choose one node based on the route set that you have advertised, and in our case, it chose node 1. And this server decided to send a call to this gateway. However, when this gateway sends a 200 OK, its route set doesn't go here, but probably might go here. Now we have a problem. Why? Because we don't really know whether this guy can reach, how this guy can find this guy. But in a stateless mode where you have all the routing information inside the SIP message, so you have all the routing information inside the 200 OK, this is very simple. You just take that information from the node and send it back to the client. Similarly, the ACK will go here. You will simply forward it to the node because you have all the information inside the packet. However, that's not always true. All modern proxies usually no longer use stateless proxies. Why? Because they want to go stateful, because they want to detect retransmissions, to do retransmission in case a node goes down and you really want to reach it. You want to have some timeout detections, and this can be done with a stateless proxy. So you have to go stateful. You have to have some transactions. You have to have timeout for those transactions and so forth. Also, if you're doing a stateless and the node goes down, you can't really recover from that because you don't really know when the call starts and where it started. When you get the buy, you might not end up the call properly and you might lose some CDR. So basically, stateless Anycast, although it might be very easy to use, it doesn't offer too much flexibility in terms of higher level applications. That's why we needed to do a solution that uses Anycast in a stateful mode. And how we've done it is, so we have the same scenario. The client calls here, goes down to gateway responds here. But now, this guy doesn't have any idea about the transaction because the transaction is only known by this guy, by node 1. But what he will simply do, it will replicate this 200 OK and its metadata to this node. This node knows everything about the transaction, so he can take all the decisions he needs. And he will be the one that will send the 200 OK. He will be the one that will establish the dialogue and so forth. OK? Having this, it's very easy to also ensure reliability. So since you are using different nodes, and you have a customer going here, if this node goes down, you probably want to fail over to a different node, right? This will be done very easy using Anycast because all you have to do is the agent that will run on this node will basically pull out the routes, so nobody will be able to reach this guy. But in order to do this, you'll have to make sure that this guy is able to properly route and properly handle the traffic from here. So this means that this guy needs to know the start time of the call and basically have all the dialogue information that this guy had. And this requires hot backups. This requires that all your nodes inside the cluster know more or less the same thing. They need to share the data and replicate data to each other so that everybody can be able to act on any time, to act on a specific dialogue. This can be done very easy. I will show you a bit later how, but imagine that you have like 5 nodes, 5 different servers that all of them know about dialogue. But that dialogue should no longer be continued because, I don't know, let's say the dialogue, the call timeout limit has reached. So you might have 5 different servers that are trying to forcefully close a call. That's not very desirable. Also, having 5 different nodes having the same data, you might run into some consistency issues because data does not instantly propagate. So in our case, we try to mitigate that, and in order to solve it, we enforce the ownership of the data. So at a certain point of time, even though there are multiple nodes within the cluster that know about the data, only one node is in charge of that specific dialogue. This means that only one node will write CDRs when the buyer is received. Only one node will time out the call if the call should be turned down. Or in the distributed user location case, there's only a single node pinging the client, because you don't want to have like 20 nodes pinging a single guy. Probably he will break. Moreover, you'll also have, in order to make sure that everybody knows everything, when a node goes down and then it gets up, he will become a joiner. This means that he will have to sync from everybody, right? So that everybody has the same data about those dialogues. Our solution was to basically go to one node that is fully synced, that we know it's synced because he's been running for a while, and get all the information from that node. Again, now that you have different nodes that all share the same data, you can say that your platform acts as unified, acts as a whole, as a single platform. This means that, for example, if you want to impose concurrent call limits, imagine you have a client that is only allowed to have 10 maximum concurrent calls, and he starts doing 5 calls on this node, but somehow it ends up on this node making 5 more calls. That's fine, because he didn't reach the 10 calls limit. However, if he tries to go on this node and do 2 more calls, well, that's not okay. And you want to cache this case and close these 2 or reject these two calls. Similarly, you have the same problem in your gateway interaction. So for example, imagine you have a gateway that allows you to only have 500 maximum calls per second here. And you start sending 300 calls per second from this node, and then using the same gateway, you're starting to send 200 calls per second from this node. This is all fine because everything is within the limits. However, if this node starts to send 100 calls per second, those calls will probably be rejected, right? And in order to avoid this, you want to catch, in order to avoid the round trip, you want to catch this case and fail over probably to a different carrier or a different gateway that doesn't have this limit. So again, in order to do that, you'll have to share the dynamic data, the calls dynamically between all the nodes within the platform. Otherwise, you might run into the limits. These are some of the problems that we've met and we've solved, and most of them are solved. Actually, all of them are solved using the OpenSIPS cluster. OpenSIPS cluster is the low-level, let's say, engine that allows us to build these nice applications, and it's used to have to group multiple nodes that behave similarly into a single cluster that acts as a whole. All the nodes within the cluster share data, and although we've been doing this using databases, now we decided that databases are no longer very efficient, and we've done our own protocol that we think is very efficient because it's binary, it's based on TCP, it's asynchronous, you don't block trying to send data. It uses Heartbeat packages in order to ensure that everybody knows the entire topology. Now, it supports different topologies, very diverse. So for example, you don't need to have a full mesh in order the cluster to work. You can have you can have something like this. Also, you have link redundancy in the cluster. If this link goes down, two will be able to reach for using 5. So nothing happens. If a link goes down, everybody is still in sync because they can use each other to route. And it's very simple to join. All you have to do in order to join the cluster, you have to know one node within the cluster, connect to it, and then you'll start discovering the entire cluster. He will say his neighbors and his neighbors' neighbors and so forth and so on until you figure out everything. So this is the OpenSIPS cluster, and I've presented you the bottom of the cake. Now I'll let my colleague leave you to show you, to put some topping on this cake. Go on.
Right, and hi everyone, I'm Liviu Kircu. I'm a core developer of OpenSIPS. Maybe I should have introduced myself in the beginning, but we need to work on that. And we will be talking about only one of the applications of the clustering layer that's baked into OpenSIPS 2.4, which is the way and the solutions we chose in order to distribute the user location. Quick summary, are we all up to par on what a user location is in the first place, a SIP? Because, I mean, to me at least, it's a bit of a confusion in there. Because on one hand, we have the location of the user, right? Here we have Alice and Bob in London and Amsterdam, and on the registering to the service. And on the other hand, you have the act of locating a user location, the verb, right? And it's most often we talk about the latter one, so the service that locates users, and that's what we distribute. The location itself, it is just a point, a physical point. I won't get into too many SIP details and how headers and all that. We are just going to talk about data distribution models and that cater to various scenarios you might have, and those are all pre-baked into OpenSIPS 2.4, which was released in May this year. One of the first data sharing models is easy to grasp. It's full sharing. We simply assume we have a cluster of nodes that are homogeneous. They have the same data set, and whatever registrations come on one node, they get distributed to all others. And I'm going to go through two core problems and with each model and see how we've solved each of them. And the first one is, of course, high availability, because that's why we make the cluster in the first place. And here we can see an OpenSIPS cluster that has traffic balanced to it from some SBC, and it's all good and pretty up until we start experiencing some failures for whatever reason, hardware failure, software, whatnot. And in this case, thanks to the fully meshed nature of the data, the balancer can keep on pushing more traffic to whatever existing nodes remain, and the service is literally unaffected. A second problem that we had to solve is the pinging problem. And because when you start copying this data to multiple nodes, all of a sudden, all of them will start attempting to so let me go back a bit and describe the problem itself. We have Alice and Bob over there that are registering from their private networks right into the platform. And of course, there's going to be some NAT device on the way, and we have to come up with a way of maintaining these NAT bindings alive. And this is typically done using these SIP options pings that we push out from the platform back to the phones, say, one time per minute, or in order to have reachability. Of course, you could argue that nowadays people use push notifications and whatnot, but that's a whole different ballgame, and we can talk about that sometime later, or you can hit us up and we'll talk about that. But here, we had to solve this problem because plenty of businesses still rely on this model. All right, so we now have, we are trying to prevent the cluster from sending these extraneous pings. And this solution is solved right at the cluster layer. So the user location doesn't even need to bother too much about that, because the cluster is self-aware, and at any moment in time it knows how many nodes online it has and how can the pinging workload be properly spread. For example, if there's a failure, the pings will be originated and split between the remaining nodes. If you take a look, we had nodes 3 and 6 doing the pinging there, and now they have moved to whatever 1 and 4. It's some sort of a hash function. And summing up this this sharing mode, it's an excellent starting point. It's very easy to throw in there, and it's a very good solution for medium to small sized businesses. And not to mention the fact that you don't have to install any additional databases. It's a purely OpenSIPS only solution, and that's also much easier to maintain. But if you want to take things to a further level, or wait, is there any obvious limitation to it? So what is wrong about full mesh replicating data to a cluster? The obviously, I mean, not really wrong, but it won't take you so far, is that you won't be able to scale this too much. Like, you will keep adding nodes to it, and the replication effect will compound on itself. And thus you will probably going to orient yourself to a new solution once the business actually starts growing. And we took this opportunity to come up with the second mode that adds this layer of complexity, where you also have to maintain a NoSQL database, which is obviously a lot better at knowing how to share data, how to partition it, ensure redundancy, and all that good stuff. And let's quickly go through the core problems. So high availability, again, we have even less data to work with on the OpenSIPS node, so that's pretty much already taken care of. And it now moves to the database. So whatever data replication policies, I've mentioned the replication factor. That, I guess that's a bit MongoDB specific, but it probably applies to even Cassandra or other clustered NoSQL databases. And all these concerns move over there. And with regards to pinging, again, we have the layer of the OpenSIPS boxes that is self-aware and is able to build these specially crafted queries in order to extract only the subset of contacts that it should ping. So again, we won't have these ridiculous n times pings for each of OpenSIPS box that's hooked into the database. So the extraneous pinging problem is solved. So to sum up all of this, it's good for scaling. You get a lot more control with regards to where your data lives and how you scale your reads and your writes. And this is a typical use case for end platforms and large scale, possibly even global scale. As a con, I throw it in there. Maybe there's a question mark on that pinging query performance. Well, obviously, we can add on top of it, we can put some caching in there. Remember what are my pinging contacts that I should ping. But let's first see that it's a true bottleneck, and we can optimize it afterwards. And we've also added kind of a third data sharing mode. And this is geared towards platforms with a lot of data centers, where you kind of want to minimize all the data sharing that goes on between these data centers. And you want to put as little strain on the NoSQL database as possible. So we called it federated storage because the data is individual to each POB. And it's somewhat, there is still some sharing going on because you will receive calls right into a city and you will have to egress towards some other city. So obviously you cannot not share anything, but it's minimized. For example, here we have Alice that registers to Seattle, and the platform only publishes a light metadata record inside the database. For example, it looks, I don't know why it says Live but anyway, which points to her AOR and links it to the home IP she registered to, such that when she receives a call on, say, Austin POP from Bob, the service does the lookup, says, okay, I have Alice up on Seattle, so let's route the call over there, which is the only way of reaching her, by the way. We cannot directly route from Austin, even if we had the data. Okay, and the core problems, the HA and pinging, we can do a hot backup server. We can attach it to each location, and that's kind of the way to scale them. We add pairs of these in each location, and we can dynamically size each of them according to the number of the subscriber population that's in there. And the pingings are even more simplified here, because we don't have the contact data living in each location. So for example, even if over there Austin and New York would want to ping the contacts, they can't ping Alice because they don't have that data. They only know that the data lives in Seattle. So in this case, only the pings will just be generated by there. So that's solved already by itself. And to sum up all of this, it's a solution that allows you to have more flexibility and scale or go towards this deployment with a lot of data centers. Whereas the other one with the NoSQL, the one where we share all the data inside the big NoSQL cluster, is more geared towards maybe 1 or 2 large locations. An obvious con of this one is that we cannot fail over to another DC. So if we had that requirement, again, we may want to look into solution number 2. And let's look at some possible edge cases, some other questions that might arise. For example, I have this requirement. So here I plug my clients right into the cluster. I don't have an SBC. And obviously, I'm going to have to add a path to that contact. So the question is, does that path also get replicated when I spread it across the cluster? Also, you might have some attributes. Let's say, again, you attach them to contact and propagate to the cluster, or some branch flags, if you're familiar with the OpenSIPS script. And the answer is yes, yes, and yes. So all of this information is included in the replication packets, such that any of the nodes can make use of it and know these outbound proxy settings that they should route according to. And quick look on how the scripting is. It's really simple. Just configure the mode and the cluster, and you're good to go. Save and lookup will work exactly the same for any of the modes. And we plan on also adding a Cassandra driver update. Currently, it only works with MongoDB. And some credits to all the people that have helped shape the requirements for this user location. People like Vlad Payu, Eric Tami, Jared Beaumont, Adrian Georgescu, Muhammad Shaza, David Sanders, and Rudy Pedraza. All these wonderful people have weighed in and helped during online meetings and whatnot to shape this feature. And don't forget about, if you want to learn more about this stuff and get some training from our team, you can register for the OpenSIPS training on Friday, where we will be doing a lot of the newly baked features into OpenSIPS, mid-registrar, interactions with FreeSwitch, also homework capturing, all of that we will be doing on Friday. And don't forget about the bootcamp, which will be in October, late October, where there will be a full week of training with Bogdan and Flavio. And these guys have like 20 years of experience, and they can teach you everything about OpenSIPS. Go to opensips.org/training. And yeah, as a wrap up, we tried to deal with all these complex problems in OpenSIPS 2.4, and to the point where it all looks easy now. If you have any more questions, or I guess we can skip those because we're a bit ahead.
Wonderful, thank you. Big round of applause for Razvan.
And leave you. Thank you very much, guys.
Thank you.